Hi, Professor. So, for this exam, I'm gonna explain question number 2 for chapter 6 homework. Okay, so for part A, here we got this figure showing the free diagram for that square, and y and x axis, this is the distance. So the object itself move with a force of push from the left to the right, and that's all we got by far. So on part A, they asking which of the following statements currently describes the sign of the work done on the box by the force of push. So with the equation of work, we should be able to find if the force of the push, they mean this force, where it's positive or negative in this case. So let's take a look of it. Alright, part A. So we know that work is equals to the magnitude of the force times the distance times the cosine of the angle between the force and the direction of the distance. So in this case, we got this free body diagram. The force we're trying to look for is this one, force of push, and the normal, that is weight, and friction. And the box move from the left to the right. Okay, so they're asking if the work of the force of push, whether it's positive, negative, or zero. So we may use this equation in this case. And basically gonna put the force and the distance, they label it as d, so d, and the cosine of the angle of these two. So in this case, since we see that the this force is going to the right, and the distance of the object itself moves from the left to the right, as we can see here. So we may say that the angle, that there is no angle, so the cosine of theta will be 0. I mean, yeah, theta is 0, so the cosine should be positive 1. Then we may say that the work will be the product of the force times the distance. Everything's gonna be positive. So in this case, we can check positive. Then the next question, it says, which of the following statements accurately describes the sign of the work done on the box by the normal force? So we should do the same thing, but using the normal force as the magnitude of the force. So let's see. We see here that the magnitude of the force of normal force is going up, and the distance is like horizontal. Since this is horizontal and vertical, there will be an angle of 90 degrees. This is important because if we are using this equation, normal equals normal force d cosine of theta. Since the theta is gonna be equals to 90 degrees, this the cosine of 90 is 0, so everything will be 0. So work by the normal force will be equal to 0. And then yes, 0 right here. The next question is asking for the force of kinetic friction. So it's that one force that goes like all the way around. Since the move is from left to right, the friction is going to the opposite side. So the angle for this will be 180 degrees. So yeah, as we see here, it should be 180 degrees. So let's put it right here. See, yep, work friction is equals to friction times d cosine of theta, where theta is equal to 180, and this is gonna be -1. So everything's gonna be multiplied by -1. Then we may say that the work made by friction is gonna be negative the force of friction times the distance. So this is negative. So negative. Which of the following statements accurately describe the sign of work done by the box by the force of gravity? Gravity right here. So part D. So if we see here, work is basically -90 degrees, or like positive 270 degrees. So work made by weight is gonna be equals to WD cosine of theta, where theta is gonna be equal to 170, which is gonna be 0 again. So the work made by the weight is gonna be 0 in this case. Let me just check it real quick. Yep, cosine of 270 is 0. So here 0. So the next part, they're asking for us to look for figure number 2, where we see the displacement of this object going from a slope from up to down. This is the distance d, and yeah, pretty much the angle of it. So let's see what part E says. So they say you have just moved into a new apartment and trying to arrange your bedroom. You would like to move your dresser of weight 3,500 newtons across the carpet to a spot 5 meters away on the opposite wall. Hoping to just slide your dresser easily across the floor, you don't empty your clothes out of the drawers before trying to move it. You push with all your might, but you cannot move the dresser before becoming completely exhausted. How much work do you do on the dresser? Okay, so let's try to plan the equation for it. And let's see what do we got here. So where is the flash? Well, I think it looks great. Yeah. Part E. Okay. Sorry. So here we got we got a drawer of mass. I mean, they give a lot in newtons, so it will be 300, 500 newtons. The distance S will be 5 meters. They just give us that. So let's see what we can do here. So yeah, the distance we're trying to move the drawer is 5 meters, right? What we try. However, what we got is 0 because we didn't move it. So it was like what we got to move. So what they said, let's see, or equals the force times the distance times the cosine of theta. So since we didn't move anything, we may say that is gonna be equal to 0 meters. So everything's gonna cancel out. And then since we didn't move anything, the work made basically was 0 because we didn't achieve anything and we didn't move anything at all. We did like work out and like with all our might, but the work done it was 0, so we got like nothing done. So yes, the work will be 0. Because the distance was 0. Okay, so here we are, figure 2. A box of mass m is sliding down frictionless plane that is inclined at an angle, let's say theta, above the horizontal, as shown in the figure 2. What is the work done on the box by the force due to gravity W if the box move at a distance d? So here we use this figure to illustrate what we want to do. So to begin, I'll try to do a free body diagram. So this is gonna be question part F. Yeah, sorry. So part F. So the body diagram should look like, I like to do it this way because it's better for me to understand it. So we got here the normal, let me see, normal, and then the friction. Did you say there is friction? Oh no, there is no friction, sorry. Anyways, so what we got here is W itself, because it's inclined. Here we got theta. This is W. Here we got W sine theta, and this right here is gonna be W cosine of theta. And then since the object is moving like down, like we got this, since the object is going from this point to this point, and the force, we can find the force, we can use this force, W sine of theta, since this one is going parallel to the distance, so we might find what's gonna be the work of it. So yeah, that's basically the work made by the weight, sorry. So let's see what we got. Gonna be W of W equals to W sine of theta, and then they label it like distance, so like D, yep, cosine of theta. So the angle here is gonna be 0, there is no angle on it, so it's gonna be multiplied by 1, so W is equal to W sine theta distance. So basically I'll say we're down here. There is just one thing, that there is not like an answer for this like with sine. So if we know the properties of trigonometry, we may know that the cosine of 90 minus the angle of theta, whatever, it's gonna be equals to the sine of the same angle. So what I'm trying to say is, if we got this sine of theta, we may say that this property says that sine of theta is equals to cosine of 90 minus the theta. So we can convert it to have an answer like WD cosine 90 minus theta. So this will be the answer for this, in this case, WD cosine 90, the WD cosine 90 minus theta. Yep. And here this question says, per G, the planet Earth travels approximately in a circular orbit at a constant speed around the Sun. What is the net work done by Earth by the gravitational attraction between it and the Sun in one complete orbit? assume that the mass of the Earth is given by ME, the mass of the Sun is given by MS, and the Earth-Sun distance is by RS. Sorry. So that's what we got. That's answers. So let's try to draw what we got here. Margin G. Okay, so let's draw like a point, like a circle over here. Let's say this is the Sun and Earth is here. So this is the whole orbit of Earth. They're asking for the work done by Earth. It's known that the gravitational force is like attracting the objects. So in this case, the gravitational area of the Sun is attracting the Earth. So this is gonna be the magnitude of the force of gravity itself. So yeah, let's see what do we got here. So in these hints they give us, we may know that the force of attraction of two objects may be found by this equation right here. So they say that force is equal to gravity times m1. In this case, m1, let's say this Earth, and m2 Sun over radius square. They also give us a reminder of the circumference of the circle. This may be used as a distance of the circle. So they say C, the circumference, the diameter, is equals to 2 pi r. So C is gonna be equal to 2 pi r, right? Since we need to both of these to know the work, force, displacement, cosine of the angle between those two. So the force, when we say, is this, and the diameter is gonna be the distance. So the work made by Earth is gonna be equals to gravity ms over the radius square times 2 pr 2 pr cosine of the angle. So we might cancel out this 1r, and we may end up with G me ms over r times 2p cosine of theta. So we may like the answer may be this one, like this one. 2pg ms, everything looks great. However, there is something we gotta keep in mind: the angle between those two. So as I said before, the force of gravity will look like this because Earth is being attracted by the Sun, and the distance is being directed by the orbit. So the distance may be put as this vector, let's call that, yeah, it's a vector. Since the gravity is like this, the force of gravity, and the direction is this one, is doing orbits over it, around it. So the angle of these two is gonna be 90 degrees. We know what happened with 90 degrees. The cosine of 90 will be 0. So with numbers, we may say that the work made by Earth is gonna be equal to 0 joules. There is no work at all made by Earth by being attracted by the sun. So and the last one, per age, a block of mass m is pushed up against a spring with spring constant k until the spring has been compressed a distance of x from equilibrium. What is the work done on the box by the spring? So let me just turn on this paper. Okay, all we got is, let's kind of draw what do we got here. So we got a spring hanging out from the ceiling because it's being pushed up and pushed down. So this is the object, right? Then there is a force pushing up, force of push. Then the spring hanging is being compressed. So this is x. It's the distance from the equilibrium to the spring being compressed. So this is force, and this force like of the spring since it was compressed. So for this we may use integrals to know what's gonna be the work made done by the spring. So we need to use this constant unit of k to see what's the work done. So we may use this integral from the equilibrium to x, since it's the distance, and we may use the spring constant, which is k, right? This is a function of x dx. When we do this integration, the answer basically is gonna be 1/2, since it's going to from 0 to x. The first input will be 0, so we may end up with the negative. Then kx square. So this defines the work made by a spring. There is also another way to work it out by a graph, since integration is the area. Sorry. So goes from x. So this is plane. So this is basically a function of kx, as we say here. So this is k of x, this is x, oh sorry, so this is k, yeah, so this is negative k of x, this is k of x. So this magnitude here is gonna be all x values, and the spring constant is constantly going either I mean, when it's compressed it's gonna be negative. When the spring is being stretched it's gonna be positive, but in this case it's being compressed since it's being pushed, so it's a constant like this. And we may look for the area of this region right here. It's basically a triangle, so for an area of a triangle it's the formula 1/2 BH, right? So this right here, the BH base, the base is gonna be x value, and h, the height, is gonna be the negative kx, right? If we put the number, what it goes in this case, we got that it's 1/2 the base gonna be x times the height be negative kx. Then we may say that it's gonna be equals to negative 1/2 kx squared. So graphically we show that this is right, that the work made by the spring is negative 1/2 kx squared. So there is no such an answer that describes the right answer. So there is none of this, right? Yep, that's what we got here. So yeah, that's the answer for this equation. So that's it for this exam.